Hi everyone, this is Professor Mayunger and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show finite element analysis of a duct using ANSYS mechanical APDL. This duct is actually a special type. The cross section of the duct is two concentric squares with specific areas, and we'll analyze this one with a specific structured method and considering 1/8 of the object. Right, let us see the statement of the problem. The cross section of a 20 cm by 20 cm duct made of concrete walls 20 cm thick is shown in figure. The inside surface of the duct is maintained at a temperature of 300 degrees centigrade due to hot gas flow from a furnace. Outside duct is exposed to air with an ambient temperature of 20 degrees centigrade. The heat conduction coefficient of concrete is 1.4 watt per meter degree centigrade. The average convective heat transfer coefficient on the outside of the duct is 27 watt per meter square degree centigrade. Determine the temperature distribution and the rate of heat flow per meter of the duct. Let us see the drawing of that one. This is the duct. It is having two squares of size 0.6 meter and 0.2 meter. And what we have to do is we have to analyze this one by considering the 1/8 of the model. This is the model you can see. If we find result on this segment, it will be symmetric for the other remaining segments. It is having total 8 symmetric segments. We are considering only one symmetric segment and that to be analyzed. Right, let us see the drawing. So it will be started from x equal to 1 and y equal to 0. We can model this one right accordingly. So without wasting time, let us start analyzing using ANSYS mechanical APDL. First of all, we need to create a directory and everything to be saved in that directory as usual. Next to that, we need to change the title of this one, right? Naming this title as FEA 18. Okay. And to see the title, we can click plot replot. It will show the title at the lower left corner. Next to that, we need to select what type of analysis it is. It is definitely a thermal analysis. So thermal analysis clicked in. Okay. Next to that, we need to provide elemental properties and that will come from preprocessor. Element type, add, edit, delete. Let us add it. And from options, we can select element behavior plane with thickness. Okay, let us consider thickness of that one to be 1 meter. So from real constant we can provide thickness of that one, add. Okay, and we are providing thickness of that one to be 1. That will not change the results at all. Let us close it. Next to that, we need to provide material properties, right? Material models, thermal conductivity, isotropic, and it is having thermal conductivity of 1.4 watt per meter degree Kelvin, right? 1.4 watt per meter degree Kelvin. Okay. Next to that, we need to start modeling. And as I told before, we need to model 1/8 of the component. So create node in active coordinate system. As per drawing provided, first node will be created at a distance of x equal to 0.1 meter. Apply. Next node will be created at a distance of 0.3 meter. Apply. So first row is complete. Now we need to move off. So in the upward direction, next node will be created at a distance of x equal to 0.1 and y equal to also 0.1. X equal to 0.1 meter and y also equal to 0.1 meter. Apply. Next node it will be at a distance of x equal to 0.2 meter and y equal to 0.1. Apply. And final node, it will be at a distance of x equal to 0.3 and y also equal to 0.3. Okay. So all the nodes are made. We need to combine all these nodes into elements. So elements, auto numbered through nodes. We started nodes from 2 only, because first node we deleted, so we started the node from number 2. Second node, third node and fifth node will be comprising element number 1. Apply. Now second element will be comprising node number 2, 5 and 4, right? We can select node number 2, node number 5 and node number 4. Apply. Second element is made. Third element will be comprising node number 3, node number 5 and node number 6. So we can combine all these things, 3, 5 and 6. Apply. Third element is also made. Now the fourth element will be comprising node number 4, 5 and 6. Okay, so this is our element. Now we need to apply our boundary conditions, and that will be done from loading analysis type. It is a new analysis and we are considering steady state analysis. Okay, next to that we need to define loads, and from the boundary conditions we know that inside it will be having a constant temperature of 300 degrees centigrade. Outside heat will be transferred by way of convection with a convective heat transfer coefficient of 27 watt per meter square degree Kelvin at a bulk temperature of 20 degrees centigrade. So the first one, it will be constant temperature of 300 degrees centigrade. So define loads, thermal, temperature on nodes. Let us select the inner surfaces or inner nodes. Inner two nodes are selected. Okay, and it will have a constant temperature of 300 degrees centigrade. Okay, done. First boundary condition is applied. Now the second one will be at the external surface of this duct. It will be heat transfer by convection, right? So again, apply thermal convection on nodes. Let us select node number 3 and node number 6. Okay, it will have convective heat transfer coefficient of 27 watt per meter degree Kelvin at a bulk temperature of 20 degrees centigrade. So it is 27 watt per meter square degree Kelvin and bulk temperature is 20 degrees centigrade. Okay, done. So we applied all our boundary conditions. Next to that we need to solve it. So we can do it from solution, solve current ls. If everything is right, it will show solution is done. It is showing solution is done, so everything is perfect. We can see our results from general post processing, right? Let us close it. General post processing, plot results, control plot nodal solution, nodal temperature. Let us see the results, right? So this is the temperature distribution along the elements, what we considered for analysis. For the remaining objects also, it would be having same answer, right? Because these are symmetric results, these are the symmetric objects, so results should be also symmetric. And you can see the maximum temperature is obtained at the inner side and its temperature is 300 degrees centigrade, and minimum temperature is obtained at the outer surface and it is actually 43.6635 degrees centigrade. Next to that we can see like the same results in the form of listing, list results, nodal solution, DF solution, nodal temperature. You can see the temperature at different nodes. We created 6 different nodes and you can see temperature at different nodes, right? And it is better to see the nodes together with the actual nodes, right? So for that, plot nodes, these are the different nodes and we can number these things also. Plot controls, numbering, you can provide specific numbers to the specific nodes. Node numbers are off, we can make it on. Now you can see at different node numbers, node number 2 is having maximum temperature of 300 degrees centigrade. Then node number 3 at the exterior surface, it is having minimum temperature. Node number 3 is having temperature of 76.447 degrees centigrade. Again, node number 4, it is at the internal surface, it is having maximum temperature of 300 degrees centigrade. And node number 5, it is inside, its temperature is 181.67 degrees centigrade. And node number 6 at the top external surface, it is having minimum temperature, it is 43.664 degrees centigrade. And you can see maximum temperature is occurring at node number 2, 300 degrees centigrade, right? So this is the result. We can close this. Now another thing we can do, we can see the animation of this temperature distribution that can be viewed from plot controls. First of all, you can see the results, plot results, nodal solution, nodal temperature. You can see again, we can see the animation of this one. Let us see plot controls, animate, and we can see deform results. With the default setup, we can see temperature distribution. Okay, let us see this distribution. Let us see forward only. You can see how temperature is distributing from inner surface to external surface. And you can see here maximum temperature is occurring at this node number 2 and minimum temperature is occurring at node number this one, last one, right, at this location. Okay, so let us close this one. So with this one we will conclude our today's video. This was a very simple analysis of a duct using ANSYS mechanical APDL, and here in this case we considered 1/8 of the object for this analysis. Because this was a symmetric object, we considered 1/8 of the object for analysis, right? So in this analysis we found the temperature distribution throughout the whole duct, right? So this is all about today's video. Thank you so much for watching this video. Thank you again. Bye.
If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.